A continuous population exists over an interval of the real numbers. There will be a beginning number and an ending number, and everything in between is part of that population. Now, that may be negative or positive infinity where the population begins or ends. Every continuous population is defined by its probability density function. This is going to be an equation that takes every value in the population and gives it an associated density. Now, the PDF does not tell you the probability of a value occurring. In the continuous world, because there are infinitely many values infinitely close together, the probability of getting any one number is always 0. Instead, the PDF tells you how dense the probability is in that neighborhood of that value. To be a legal probability density function, you have to meet the two conditions. The first condition says that the density function, f of x, has always got to be positive or 0. That is, the graph can never drop below the x-axis. Now, the second condition is that the total area under the curve, so when we draw our graph and we look at the area between the x-axis and the graph, which will be up above, the total area has to be 1. Now, this is because in the continuous world, probability and area are the same thing. The probability that your variables between 2 points is equal to the area trapped between those 2 points on the horizontal axis and the graph up above. Now let's look at some examples. The first continuous population we want to look at today is the uniform distribution. So this particular one, we're going to be generic and have it continuous on an interval from point A to point B. So our graph is going to start at point A on the left, end at point B on the right. And we want this to be uniform in density. That is, if we take any value from A to B, we get the exact same density. That is why our graph is a horizontal line. Now, the total area under the curve, or in this case line, has to be 1. Now, since this particular graph forms a rectangle, we know that the area of the rectangle is base times height. So in order for this to be a legal probability density function, the total area under the curve, the base times the height, has to be 1. Now, we know that the base of this rectangle is the distance between point A and point B, which is just B minus A. Therefore, the height of the rectangle must be the reciprocal of B minus A. Right? 3 times 1/3 is 1. 2 times 1/2 is 1. Whatever B minus A is, we're going to multiply that by 1 minus BA for the height, and then our total area will be 1. Right? So when we say something has a uniform distribution, all we're saying is it has a probability density function of the form f of x is equal to a constant. Okay? That is, in particular, the constant is equal to the reciprocal of the distance between point A and point B. Let's look at a specific example here. So, we're being told that the ages of Phineas and Ferb viewers are between the ages of 6 and 13, and that they follow a uniform distribution. And we're asked to find the probability that a randomly selected viewer is younger than 11 years old. Okay, so the first thing we have to do is get our picture straight. So we have a uniform graph from the ages of 6 to 13. So I have a flat graph from 6 to 13. The total area of that graph has to be 1, okay, which means the base of this graph times the height have to be 1. Now, we want our distribution to go from 6 to 13, which means my base is a width of 13 minus 6, or 7. Now, that tells me that the height must be 1/7. Since this particular rectangle is 7 wide, the height has to be 1/7, and then 7 times 1/7 is going to be 1. So the equation for our density function says, as long as x is in our range from 6 to 13, the density, or the height of the graph, will be 1/7 the entire time. So let's tackle the specific problem. What is the probability that a randomly selected viewer is younger than 11 years old? So here's the picture we want to look at. Now, again, when we look at the entire population of potential viewers, right, they have a uniform distribution from 6 all the way to 13. So we have the same rectangle that we've had before. Right, uniformly distributed with a height of 1/7, right, for all ages from 6 to 13. And notice here, yes, it's labeled 6, 7, 8, 9, 10, 11, 12, 13, but that does not mean that ages can't be between 6 and 7 or 7 and 8 and so on, right? Because we're saying anybody from 6 to 13 and every possible age in between is part of this population we're studying. So we want to find the probability that a viewer is younger than 11. So on the horizontal axis, right, I want the variable x, the age, to be between 6 and 11. By definition, because this is a continuous population, the probability that a viewer is between 6 and 11 years old is equal to the amount of area trapped between the x-axis and the graph and the values of x equals 6 and x equals 11. So the blue shaded rectangle represents, right, the probability that a random viewer will be less than 11 years old. So we already know the height of that rectangle, right, is 1/7, and the base, since we're only going from 6 to 11, that's 5 wide. The base is 5. So the probability that a viewer is younger than 11 years old is simply 5, the base of the rectangle, times the height, which is 1/7, or 5/7. Every uniform distribution works the same way. First, you determine the density function, the height of the graph. That height will stay constant no matter how many questions you're asked about that variable. Once you know the height of the uniform distribution, then you can be asked to find the probability of lots of things happening. Here, we could be asked the probability that a viewer is between 9 and 10. And then we need the area under the curve between 9 and 10. But the height would stay 1/7 because our viewers, population-wise, stay between 6 and 13 the entire time. Now I want to look at a completely different continuous distribution. And this is a family known as the normal distribution. Now, a normal distribution is determined specifically by its two parameters, mu and sigma. Right? Mu is the population mean, and sigma is the population standard deviation. Right? Now, normal distributions are defined on the interval from negative to positive infinity. So our values can literally be any real number between negative and positive infinity. So the possible values of mu would also be any number between negative and positive infinity. Now sigma, as you call, is your standard deviation. That tells you how spread out your population is. So your standard deviation has to be greater than 0 for us to have a normal distribution. Otherwise, we only have 1 point if your standard deviation was 0. So there is no upper limit on how wide or how spread out your population can get. So mu is between negative and positive infinity. So infinitely many choices for mu. Sigma is greater than 0, infinitely many choices of mu. So literally there are infinitely many different random variables or populations that are normally distributed or have a normal distribution. Okay? Now, the way we tell them apart is by their specific values of mu and sigma. The total area under the curve is 1 because that is a property of every continuous probability density function. Now, like we said before, right, every continuous population is defined by its specific equation, by its probability density function, and that's the same thing for normal distributions. Here is the equation for a normal distribution. Now, it looks really bad. I'll admit that. Okay? But when we say something is normally distributed, ages are normally distributed with a mean of and a standard deviation of, fill in your favorite numbers. Or IQs are normally distributed with a mean of 100 and a standard deviation of 15. When we say those variables are normally distributed, all we mean is that they have a probability density function of this format. Now, the graph of this particular equation is symmetric and centered at mu. And that's what you need to pay attention to. Okay? is that the shape and the features we're going to have on our normal distribution graphs all come from this equation. So here's what the graph looks like. It's the bell curve. Centered at mu. It goes off to the left to negative infinity, to the right to positive infinity. We have our variable. Now notice in the bottom right-hand corner here, we've labeled the graph. Right? So this particular graph, our variable is x. Okay, so I'm going to say this is a standard a graph of the variable x. So these values on the horizontal axis represent the possible values of our random variable x. These are often called raw scores when you're working with a normal distribution in particular. Now, the curve itself is the graph of the probability density function. So I want to look at a special case here, right, of the normal distribution, known as the standard normal distribution. So a couple things. First of all, I want you to notice, we're talking about the special case where mu equals 0 and sigma equals 1. Now, because this is used so much in statistics, instead of calling our random variable x, we're going to call the random variable z. So on the graph here in the bottom right-hand corner, right, you notice the little z label. So that's saying this graph is of a standard normal distribution. The mere presence of the letter z tells me, A, I have a normal distribution, so my graph is going to be a bell curve centered at the mean. And on top of that, the mean is 0 and the standard deviation is 1. All of that is part of being a standard normal distribution. Right? Now, these values on the horizontal axis, again, those are the values of your variable z, commonly referred to as z-scores. So a z-score is simply a value from a population that has a standard normal distribution. And again, our graph up here is the graph of the probability density function. So there's only two things we have with any continuous population. Right? You have the values of the variable down here on the horizontal axis, and then you have the area under the curve, which is the probability. So anytime we have a application where we have a continuous population, we've looked at the uniform, right? Now we have the standard normal. Okay. There are two other populations known as the student's t and the chi-square distribution, which are going to be used in this class. Okay. All of them are continuous populations. On the horizontal axis, these are our values. Right? And up above, between the axis and the graph, we have the area under the curve, which is representing probability. So we're going to be asked to either find the probability, find the area under the curve, given our values on the horizontal axis, or to find values on the horizontal axis that meet a specific probability condition. So like, what z-score separates the bottom 10% from all other z-scores? Now, often when we talk about a value, all right, of our variable that meets a particular probability situation like that, like what is the z-score that separates the top 25% from the bottom 75% of z-scores? Sometimes those are referred to as critical values. So that's a term you're going to hear a lot this semester. So now we want to find the probability that z is less than 2.35. So we want to find the area to the left of 2.35. So first thing I'm going to do is look at my graph. I have a standard normal graph, bell curve, centered at 0. Notice in the bottom right-hand corner, we've labeled this as z. And the graph goes off to the left to negative infinity. Z-scores go to the right to positive infinity. 2.35 is over there somewhere to the right of 0. We want to find the probability that we are getting a z-score of 2.35 or less. So we're going to use our calculator's normal CDF function. Now we need to tell it what part of the graph we want. So we're going to start by telling it our lower limit, which in this case is negative infinity. And TI did not program an infinity key. So it is programmed to recognize when you tell it that you want 10 to the 99th power. Okay, so we're using our scientific notation. And I'll show you how to do this on your calculator in just a second. right, that it recognizes that as infinity. So we want to go from our lower limit on the left, always start on the left side of the graph. The part you want, lower limit starts at negative infinity for this particular case. The upper limit, we want the graph to end, or the area, the part of the graph we want, is going to end at 2.35 in this case. Okay. Now when we do this on the calculator, we're going to get approximately 0.9906. Okay, now let me show you how to get this number with your calculator. Okay, so right next to the clear key is our variables key, and that's what we want. Right above that it says distribution, DISTR. So we're going to go second function, distribution, or variables key, and here we're going to find our normal CDF. We want to select that, and then we're going to input our limits. Again, it's negative infinity, so we want the negative key, not the subtraction key. And then second function, comma, is where we're going to find our scientific notation. That's the E. Okay, yeah, it says double E on the comma, but it's our scientific notation. And then we're going to tell it 99. So again, that negative E 99, that's negative infinity. Our upper limit, 2.35. Okay. We're going to tell the calculator our mean and standard deviation, so 0 and 1. And again, this is for those of you with the newer TI-84 Silver Edition Pluses. All right, I'll show the rest of you how to handle this if you don't see this menu right now. All right, everybody's going to start the same way to get to the normal CDF function. All right, and then we got to tell the calculator our limits. Okay, so when we execute this function, all right, we should see the 0.9906. And that's what we said the answer should be. So for those of you who have the TI-83 or some of the older 84 Silver Edition Pluses, right, when you do the second function distribution normal CDF, it's going to come straight to this screen. It's not going to prompt you for the entries. So you're going to tell it after that your lower limit, negative E 99, again, same way we did before, and then comma 2.35. Okay, so the comma key, right, and then 2.35. So everybody starts the same. Second function variables, choose normal CDF. Some of you get a menu. Some of you have to just manually enter these in. And remember, that's lower limit, comma upper limit. Either way, whatever model you have, you're going to get this same answer. For the second example, we're going to find the probability that Z is greater than negative 2.91. So again, I know it's Z, that means standard normal distribution. Mean of 0, standard deviation of 1. Draw my bell curve, centered at 0. All right, label the bottom right hand corner, Z. And I want to find the probability of being negative 2.91 or higher for my Z score. Again, Z score is on the horizontal axis. So the probability I'm looking for is equal to the shaded area. So to find this area, I'm going to use my calculator. Again, normal CDF function. All right, my limits are going to be from negative 2.91 to positive infinity. Okay. So I want you to pause and practice. I want you to enter in the normal CDF, negative 2.91 to positive infinity in your calculator. So pause the video now and make sure you can get the correct answer. So hopefully you got 0.9982. Again, if you're having trouble with the calculator, look back at the previous example we did where we walked you through it. For a third example, right, we want the probability that Z is between two specific numbers, 0.48 and 1.55. So again, draw my graph. Probability that I'm between 0.48 and 1.55 is equal to the area trapped between those two Z scores on the horizontal axis and the graph up above, the probability density function. All right, so it's your turn. Again, what do you need to do to find this area? So hopefully you put in your normal CDF, again, lower limit, upper limit, and when you do that, you should have gotten the answer of 0.2550. So we've done the only three possible problems I can do where I've given you a z-score or z-scores and say find the probability. We found the probability to the left of a number, to the right of a number, or between two specific numbers. Okay? So, all right, so we have used our z-scores to find probabilities. All right? Now I want to look at how do we use probabilities to find corresponding z-scores. Specifically, we want to find the 83rd percentile of a standard normal distribution. So by definition, we're looking for the z-score that is bigger than or equal to 83% of all z-scores. Now the bell curve is centered at 0 in this case, which means we have perfect symmetry to the left and the right of 0. Half the area is to the left of 0, half the area is to the right of 0. So that means 0 is the 50th percentile. So 50% of all z-scores are 0 or less. Okay? Now we want the 83rd percentile. We want it to be bigger than 83% of all z-scores. So it's got to be somewhere over here to the right of 0. So this is the point that separates the bottom 83% of all z-scores from the top 17% of all z-scores. Now, previously we've already known our z-scores and we wanted to find the probability and we used the normal CDF. Now we want to undo this. We know our probability of 0.83 and 0.17, two probabilities related to each other, and we want to use those to find the z-score that fits this situation. Okay, so I want to undo or invert what the normal CDF would do for us. So we're going to use the function on our calculator known as the inverse norm. We're going to find this on the same menu where we found the normal CDF, just a little further down. When we use the inverse norm, we have to tell the calculator the area to the left of the critical value. That's how they programmed it, so that's what we have to do. Okay? And when we execute this, we're going to get 0.95. So 0.95 higher is the z-score. Right? It's not a probability. So if we picked our z-score at random from the world of z-scores, there's an 83% chance the z-score we get would be 0.95 or less. And there's only a 17% chance that the z-score we would get would be 0.95 or higher. All right, so we're going to go back to our distributions. So we want to hit second function and then the variables key. All right, so second function variables. This is going to bring up our menu. We want to go to the inverse norm. Okay. Now, once we make our selection, if you have the newer model, it's asking you specifically for the area, and we tell it the area to the left, always to the left of the point we want, which is 0.83. Right? And again, if you're seeing this menu, you want to tell it the mean is 0 and the standard deviation is 1. We know that inherent from the fact that we're dealing with z-scores or the z-distribution. Okay? And so we're going to crank this out. Now, if you have the older models, you're not going to see this menu. I'll show you how to handle your calculator in a minute. You're going to go to the same place, right, to get the inverse norm function, but we'll see something a little bit different. Okay, and there we go. Rounded to 2 decimal places, this is 0.95. So for those of you with the older model, when you hit second function distribution, it would have come up with this inverse norm and an open parentheses. Right? And then you're going to type in just the area to the left. Okay, so instead of getting the menu that asks you for the area, you have to remember to tell it the area. Okay? Now your calculator will assume the mean is 0 and the standard deviation is 1. So you just have to do inverse norm of 0.83. So now we want to find the 17th percentile of the standard normal distribution. So again, the graph is going to have, right, your percentile is definitely going to be the z-score you're looking for is less than 0, because less than half the values need to be lower than this. Okay, so we're going to use the inverse norm of 0.17. Right, I want you to pause right here. I want you to go back to your calculator, right, and do this inverse norm function. Hopefully you got negative 0.95. Okay. Now I want you to pay attention to what just happened. In the previous example, we were looking for the 83rd percentile, right? And the z-score was positive 0.95. Now I want the 17th percentile, and the z-score was negative 0.95. That's not a coincidence. If you look at those two graphs, they're exactly flipped images of each other. And because we have symmetry, right, if you go the same distance to the left of mu, so here if we go off to negative 0.95, the area left in the left tail is going to be the same as the area to the right of positive 0.95, again, because we have symmetry. Okay, so let's look at one final percentile, although it doesn't look like it's percentile, but it is. So the author's notation here, he's using a z with the subscript, numerical subscript. So by the definition of the way he's using things, this subscript is always the area to the right of your critical value. So by asking you to find z of 0.10, essentially saying find the z-score where the area to the right of it is 0.10. Now this does mean by definition the area to the left of it will be 0.90. So this is saying find the 90th percentile. So our graph is going to look like this. We want the point that separates the bottom 90% from the top 10%. Okay? So now that you have the graph and you know what this terminology, this notation is saying, all right, I want you to pause and practice again. So it's your turn to find this particular z-score. Okay, so hopefully you did inverse norm 0.90. That's the area to the left. And when you did that, you should have gotten 1.28. If you have any questions about the topics covered in this video, or anything else that's happening in your statistical reasoning class, talk to your instructor, go to their office hours, or take advantage of the free tutoring available in the Math Tutorial Center. Good luck, and go Vols!